Hello, everyone. Welcome back to Geo 572 Advanced Hydrogeology. Today we're going to discuss uh, essentially matching models um, to observations and exploring model sensitivity to um, changes in parameters. And these are things that groundwater modelers do all the time and that you guys are doing for your final project. So to do that, let's get started and let's think about a simple groundwater model that we might be setting up. And a simple system that we're trying to model. So first of all, let's just think of a really simple system, say a two-dimensional cross-section that of the groundwater model that you're doing for your final project. Okay, so we're going to consider this simple model. So or simple setting. So let me just draw really quickly a simple cross section. We got some kind of mountain range coming out. We've got a river, right? And we're interested in being able to model groundwater flow in this system to the river. And let's add some, let's add a bit of stratigraphy here. So we've got an upper aquifer, we've got a semi-confining layer, and then we've got a lower aquifer. All right, and so upper aquifer and lower aquifer. So here we have K1, hydraulic conductivity of this upper aquifer, and S1, storage coefficient of this upper aquifer. Here we have K2 and S2, and here we have K3 and S3. So the hydraulic conductivities of these different units and the storage of these different units. All right, and let's say that we're interested in being able to calculate the amount of groundwater discharge into our stream, all right, from both of these units. Okay, so let's say, and this is the case in most settings, that we have some wells, right, that are finished in these aquifers at a few places. And in each one of these wells, we've got a measurement, all right, a real measurement of head. So this is H1, H2, H3, and H4. All right, so we've measured the head in these, in all these wells. Okay, so this is the real world, all right? And we've got this groundwater system, and then we've measured these heads here. And what we're interested in is we want to build this numerical model, right? So for example, we might have this square. Actually, let me change the color here. I'm going to make this like a light. Let's go with orange. No, I've already done orange. Purple. All right, so we're going to make this, you know, this numerical grid. And let's say this is what our model looks like, right? And remember that this model is a mesh, right? And so it's got all these squares. All right, and what we want, if we want to use our model to say calculate groundwater flux, then we need to make sure that it's behaving like the real world, right? So our goal is to have our model behave like the real world. All right. So what do? We in order to do this, we can adjust parts of the model or parts of the boundary value problem solution such that our model, so we can adjust our model ingredients so that our model gets closer to reality. And the ingredients that we often adjust or can adjust, all right, are many. They're basically anything we've used to build our model, all right? But the ones that we often adjust and the ones that have the most uncertainty or the ones we know the least are things like the parameters, all right? And here, our parameters would be K1, K2, K3, and S1, S2, and S3. All right. We could adjust boundary conditions, right? We might adjust, we don't know what all the boundary conditions are, and we might play with the values, for example, of recharge, which we don't know well. All right. And we can adjust anything that goes in here. We could adjust the spacing of the grid. We can adjust the domain. We can adjust how we drew our parameters. We could adjust like the number of layers, all right, or their thickness. There's a lot of things we can adjust. But the most common ones that we do, all right, is we build our conceptual model, and then the things that we often adjust are parameters, all right? And remember that parameters, if we look at our equation here for groundwater flow, remember, recall, if this is our groundwater flow equation that we're solving, just as an example, all right, remember that this is the dependent variable, all right? So H is our dependent variable. T, X, and Y are independent variables. All right, that means X doesn't depend on Y and X doesn't depend on H. All right, X is just X. All right, but H, the hydraulic head field, it depends on where you're at. So it depends on X, right? All right, so we have our dependent variables, our independent variables. And then these guys are the parameters. They control how our equation works, but they're not a variable that we're solving for, all right? Which is our dependent variable, and they're not something that describes how that variable is mapped into space. All right, so these are the parameters, all right? And these are things that we often play with, all right? Okay. So our goal is to make our model match reality, all right? And we're going to do that by varying, all right, portions or ingredients of our model so that our model replicates reality. And so what do I mean? All right, what do we mean by replicate reality? Well, that's a really important question and one that's not easy to answer, but is super important to understanding how your model behaves, all right? And should be based on the purpose of the model. All right. But one way that is common is our model is solving the groundwater flow equation. The dependent variable here is H, right? Dependent variable is H. And what we want our model to do is for the modeled head, all right, we want our modeled head to match our observed head. So our goal here is for our model to match the observed head. We want our modeled head to match our observed head. And I'm just going to rewrite this because this is like illegible. All right. So that's what we're trying to do. Okay. Okay. So how How do we measure? How do we measure the match? All right. Well, this is another big question and is not straightforward. And there's a lot of different ways it's done. But most commonly, using what we call the least squares. Least squares residual. All right, and the basic idea here is, let's say we have a bunch of heads. So we have, let's say here we have observations, H1, H2, H3, and H4, right? So we have H1, H2, H3, and H4, right? And least square says, what I do is I take H1m minus H2m minus H3m minus H4m. All right, I take all these differences, I square them, and I add all these squares together. All right. And then I take the square root of all of that. All right, so I'm just gonna, the least squares is you take the difference between your observed head and your modeled head, all right? And you square that difference, you sum all those differences up, and then you take the square root. So in notation, math notation, we might say the least squares residual R is equal to the sum of I equals 1 to NO, the number of observations, of HI minus HI modeled squared to the square root. All right. All right. This is the least squares residual. Now, we can think of these heads. So we could also think of this, that H is a vector of all my heads, H1, all my observed heads, H2 to Hn. So this is a vector of observed heads, all right? And we could think of Hm as a vector, H1m to Hnm. And this is a vector of modeled heads. All right. Okay. So it turns out that in vector math, the least squares residual is the same as the L2 norm, and it's essentially a measurement of the distance so R is equal to this double bar is the math notation for a norm, all right? And this is called the L2 norm, all right? And it is the distance, the Euclidean distance between these vectors. All right, and you know this implicitly because you've learned your whole life the Pythagorean theorem, right? And that says that if I've got these two legs of a triangle, then C is equal to the square root of A squared plus B squared. And A, we can think of the difference in, well, C is the distance between these 2 points, all right? And we calculate the distance between those 2 points as the sum of the difference between A and B, okay? And here, this is just for a space that only includes distances in X and say Y, all right? But this is an n-dimensional space. So the bottom line is that that the least squares residual is actually what we call the L2 norm between these two vectors, one vector of observed heads, one vector of modeled heads. And all that represents is a distance in some sense between these two vectors in a space that has n dimensions, all right? However many observations you have, that's how many dimensions this space has. All right, so when we match a model, to reality, what we really do is we minimize the least squares residual all right, which is the same as minimizing the distance between those two vectors, between our observations and our modeled heads. Okay, so that's our goal. And all we're really doing is we're saying that the way we think about our model matching reality is that we're going to minimize the difference between the modeled heads and the observed heads. And we can think about that as minimizing this distance between these two. Okay, so let's go on and say that we can conceptualize our groundwater model as a generic operator, all right? And what do I mean by an operator? So I'm going to call this model operator, and it's a generic operator, and it is A. And by A, what I mean is that this operator takes our parameters, K1, K2, K3, S1, S2, S3. It takes these parameters and all the other information, all right, that we have, and it produces head, all right, a field of head. So we can think about this operator as some generic mathematical thing that maps, all right, takes the models, the modeled parameters, simulates a groundwater flow field, and produces a head field, all right? So if we let all our parameters be equal to some vector m, so m is this vector, k1, k2, k3, s1, s2, s3, all right? M is this vector of our parameters. Then we can write a general equation that says A, this operator, dot M, all right? We apply our operator to these model parameters, and what we get out is our modeled head field, all right? Okay, so we've got these parameters. Our model, basically our groundwater model, takes these model parameters and it produces a head field. All right, and we remember our goal is that we want HM minus H to be 0 or as low as we can get it. All right, we want the distance between our modeled heads and our observed heads, so our L2 norm to be 0 or as low as we can get it. So if I insert star into my equation, I get A M minus D, A M minus H is equal to min. Okay, so this equation essentially sums up what calibration is doing. All right. And our goal is to minimize the residual between our modeled heads and our observed heads. All right. And we're going to do this by changing. So we minimize AM minus D by changing M, all right? And recall that M is all these So recall that M is basically just these parameters. So our basic idea here is that, we want to vary K1, K2, K3, S1, S2, S3 in such a way that we minimize the difference between our modeled and our observed heads. All right. And I keep doing D, and here we should be using H. Now, there are lots of ways to automate this. All right. And in a perfect world, all right, in a perfect linear world, then we want to say that AM minus D is equal to 0. And so we can do AM is equal to H. I'm going to just do a little bit of linear algebra here. And if you don't know linear algebra, you can always remember that as long as I do the same thing to both sides of the equation, everything's okay. So here I've multiplied by AT. Don't worry about it if you don't know, but if you do, it's the transpose of this matrix A, all right? And then I can solve for M, the perfect set of parameters that fit my data completely as A transpose A inverse to the -1 times A transpose H. I added an extra A here. I just multiply A transpose by this side, A transpose by this side. So A transpose A transpose H. All right. And this in this perfect world would give me M that perfectly matches reality. Or minimizes all right. And this gets called the least squares solution. Okay, so in most groundwater systems, we're not so lucky that we can do this thing where we can just say that I can perfectly find this set of parameters M by this least squares regression, all right? And so what we do, groundwater is not perfect. All right. And so finding M, finding the M such that R, our residual is minimized is hard. And there's a whole field of study in how we go about best trying to find M. All right. So here we're not going to do that. We don't have enough time. I wish we did. It's so fun. But what we're going to do is called manual calibration. All right. And what manual calibration is essentially by hand vary K1, all right, K2, K3, S1, S2, S3, all right, and minimize H M minus H2. Minimize the least squared residual. All right. So in order to do this, you've got to be able to pull off you need H. All right. That's all your observed heads. Okay. You need, actually, I'm not going to write you need every time. So you need H. You need HM, the modeled heads. And very importantly, at the observation locations. Remember, if we come back up here, your groundwater model can give you a head at any point in here, right? You need to be able to pick off out of your model the head at each point that you have an observation, okay? So that's the most critical point for you guys, is to be able to pull out the head at each point. You have an observation. Okay, in ModFlow, probably the easiest way to do this is via the well package. All right, you set up a well package for each place that you've got an observation. That well doesn't have to pump, but the well package will put out data for the head at those points. There's other ways you could skin this cat, all right? You could just take the head field and match it to the locations of your observations, whatever. But you've got to be able to pull these out. I would start off with looking at the well package. All right. So manual calibration, you go in, you've started off with some set of values for K1 through S3. All right. And you go in and you vary these other, you vary these parameters until you minimize the difference between the modeled and the observed heads. All right, so you got to be able to vary a parameter, run your model, calculate the residual. All right, so basic sequence is vary M, usually one parameter at a time. Run model. Three, calculate R. All right. You look at what happens to R. If it gets bigger when you vary it, let's say you increase K1 and R gets bigger, then the next time you're going to change and you're going to lower K1, right? And hopefully R will get lower. If R doesn't get lower, if no matter which way you change K, R gets bigger, K1, then you know you found the optimal K1. All right. So if R gets bigger or R gets lower, change K. Change M in lower direction. R higher in both directions. Stop. Right? Then you can't, if no matter what you do to that K means that you get a higher residual, that means you're at the best K you can be at. And then you repeat this for each one of the parameters. All right. And you're going to have to iterate through, and it's horrible. All right. And that's why more math is better. But if you know how to do a full manual calibration and you don't want to, or if you know how to do a mathematical calibration, all right, and you want to optimize M because the power of linear algebra is at your fingertips, you do not have to do a manual calibration. But if you don't have the power, then you're going to have to do a manual calibration. All right. And that's what I want you guys to do for your model. Now, let's talk about the sensitivity. So encoded in this is model sensitivity. And you can think of the model sensitivity as the change in the residual per change in model, or in the model parameter, in some model parameter. That's not a bar, this is an individual model parameter. All right. So for example, in our example, the change in the residual for a change in the hydraulic conductivity field of the top layer. All right. So your sensitivity is this measurement for each one of your parameters. And what you'll find is that for some params, it doesn't matter, like K1 or K2 or K3, our model could be very insensitive to it. That means that we could assume a large range of values for K3, for example, and our head measurements don't change very much. All right. So what that means to us is that our model is insensitive to K3. All right. And we're just gonna, then we just pick a value that seems reasonable, but our model doesn't allow us to decide what the best value of K3 is. So when the change in the residual per change in model parameter is low, our model is insensitive. Insensitive. All right. But for some parameters, dr dmi will be large. All right, and what that means is if, let's say I change K1 a little bit, all right, my residual either gets really high or a lot higher or a lot lower. That means I'm very, like, just a little bit of a change in that parameter drastically changes how well I fit reality. All right, so here I'd be sensitive. All right, to the value of that parameter. And my model then actually lets me know very well what the best parameter for that model is to fit reality. All right, and so these are usually reported for each parameter. So you'd have a set of parameters K1, K2, K3, K4, S1, S2, S3, all right? And then you would report dr, dk1, dr, dk2, dr, dk3, dr, ds1, dr, ds2, dr, ds3. All right, so this is what a sensitivity report has. Now, if you're smart, you'll realize that DRDK1, DRDK2, DRDK3, DRDS1, DRDS2, DRDS3, if you calculate that, then you know which way you should vary each one of these parameters to reduce the residual. All right, and then you can update the parameters. You could then calculate all those things again. And update again, calculate sensitivity, update again. All right. And generally, we report the sensitivity near our optimal parameters. All right. So in general, you would manually calibrate a model, and then you would tell me what the sensitivity at that optimal set of values is to each one of those parameters. So in general, we calibrate, then calculate sensitivity at the optimal parameters. Okay, so the bottom line is what we're after here is a model that best reproduces reality, all right? We're gonna do that by minimizing the difference between observed and modeled heads, all right? That's the same as minimizing the distance between those two vectors, all right? Or minimizing the least squares residual, all right? So your goal, your first goal is to be able to run the model and calculate the least squares residual, all right? And then in order to calibrate, you modify the parameters and you recalculate H, and then you recalculate the residual, all right? Once you've calibrated, you figure out the sensitivity, all right? And you say, how sensitive am I to each one of these parameters? All right, if I have a small sensitivity, I'm insensitive. If I have a large sensitivity, I'm very sensitive to the value of that parameter. Okay, good luck. Have fun in your calibration exercises.